Hello, everyone. After a short summer break, we are back with our IRENA Insights webinar series. So welcome and thank you for joining us. Today, my name is Martina Lyons and I'm from the IRENA Innovation and Technology Center in Bonn, Germany. For those of you who are joining us for the very first time, let me introduce you to our webinar series and also to our organization. So IRENA is an intergovernmental organization. We have currently 168 member countries and another 16 countries are in their accession process. And we support all these countries in their transition to a sustainable energy future. And because our analytical work and our engagement with our members generates a lot of valuable insights, we are constantly looking for more and different ways to share those insights with you. And that is why we have launched this webinar series, which we run every other week, usually on Tuesdays. We started in January 2020, so before pandemics proliferated many virtual events. And so far we organize over 40 webinars on various topics, and you can check them all on our IRENA events website and also on our YouTube channel. We appreciate that there are a lot of other deep dive webinars out there, but what we are trying to do here is, on contrary, to keep these webinars short. So they last approximately 30 minutes, which means we clearly cannot cover everything, but the idea is to give you enough to decide whether you want to delve deeper into the topic. And for that, we signpost in our presentation further sources of more in-depth information to help you to do that. So next slide, please. So today, while you enjoy your coffee or bagel in the next 30 minutes or so, I'm very excited to say that we are going to hear from my colleagues Arina Anisi and Gayatri Nair. They are both our power sector transformation analysts, and they look behind any bottlenecks that may hinder the transformation, particularly of power system with high share of variable renewables. Gayatri and Arina will share with you key takeaways from the recent IRENA report on grid codes for renewable power future, which is an update from their 2016 version. But before I hand over microphone to both of them, just very briefly, usual housekeeping items. Next slide, please. Perfect. So we are recording this webinar, and we will post both the recording and presentation slides on our IRENA events website within the next 48 hours. And you are all on mute. If we have time at the end, we might take some of your questions. So if you want, please share those questions in the chat section. And now, without any further ado, let me welcome Arina and Gayatri. Ladies, welcome, and over to you.
Thank you very much, Martina, and hello, everyone. It's a pleasure to be here today with you to present our IRENA Grid Code report and the main findings. IRENA released the first grid code study in 2016, and earlier this year we published an updated study, Grid Codes for Renewable Powered Systems. This updated report, it's not meant to replace the other report, but rather to complement it, and it contains the latest developments and good practices to develop grid connection codes for power systems with high share of variable renewable energy, mainly with high share of wind and solar PV. While it's also a standalone, it's a very comprehensive standalone report that includes most important topics related to grid codes, for how to develop grid codes, to the technical requirements and how they evolved over time, what is the connection between grid codes and ancillary services, the importance of grid codes, the importance of regional grid codes and how to ensure compliance of grid codes, and the last chapters focuses on guidance for designing grid codes according to some parameters of your system. Just to make clear from the beginning, the scope of IRENA work on grid code, it's focused to connect grid connection codes, which are the minimum technical requirements that VRE generators and other assets need to meet to be granted grid access. There are also other kinds of grid codes, such as market code, operation codes, but are not covered in our study. We have, for the purpose of this short webinar, we have boiled down the entire study to 5 key messages that we will try to explain to you during the next 20 minutes. So first, grid codes should be technologically neutral and should evolve to meet system needs. Grid codes should enable innovations to connect safely to the grid. Grid codes requirements need to be tailored to country system context. There is no perfect grid code that fits all systems. Also, we will touch upon the regional grid connection codes and its importance to facilitate international power trade and ensure competitiveness. And last but not least, an imperfect grid code is in many cases better than no grid code at all. So let's go to one by one to this key message and explains what stands behind them. First, grid codes should be technologically neutral and should evolve to meet system needs. The power system, it's evolving, mainly given by the introduction of high share of variable renewable energy in the system, which introduces challenges to the system operator. As you know, variable renewable energy are variable. Variable renewable energy, besides being variable, they are also uncertain. They are location constrained and inverter based, replacing also a lot of conventional synchronous generation technology. This itself changes the dynamic behavior of the power system to events. Furthermore, there are three big trends, innovation trends observed in power system that are bringing the system in a new, different direction and changing its dynamic. These are decentralization, given by the increasing deployment of distributed energy resources, small assets that are connected next to the consumer and are turning the consumer into prosumer, more active participants. Then we have digitalization, digital technologies that are helping to connect more devices, to collect data, monitor, and enable faster response, better management of assets. And electrification of end-use sector, it's a way to help decarbonize other sectors, like mobility sector with electric vehicles, building sector with heat pumps, and they also help maintain and avoid curtailment of VRE. However, all these trends are growing in the power system, are growing the power system in a new and different direction. And all this comes to a cost to the system. The system operator has to ensure that the system is both flexible and stable. Flexible means to accommodate the frequent imbalances between demand and supply, and stable to be able to recover in event of any contingency. So the power system transformation calls for evolving grid codes to make sure the system operators can fulfill these functions. Here it's a very quick comparison between the previous state and the new state of the power system. As I mentioned, from a more regulated generation influx to a variable renewable energy, from more synchronous machines to inverter-based resources, from large-scale power plants to a much more distributed generation in the system, flexible generation, more sources of flexibility in the system, from consumer to prosumer. So all these changes are calling for new grid codes, and this is the focus of our report. Here you can see a visual representation of the relationship between these three innovation trends: digitalization, decentralization, electrification, and the role of grid codes in this transformation. Both decentralization and digitalization require better harmonization and interoperability of the system, and grid codes can ensure that. Digitalization can cause cyber attacks, and new grid codes are formulated now to prevent these events in the system. Also, decentralization and electrification require new standards, and grid codes can define these new standards and can also enable provision of new ancillary services, which would also enable higher flexibility and a functional, a better system with high share of variable renewable energy. Last to mention here is that grid codes should specify the requirements in as much as possible technologically neutral manner to help avoid the introduction of technical barriers for individual technologies and to allow users to adopt the most economically efficient technical solution. I will give now the floor to my colleague Gayatri that will lead you through the next key messages.
Thank you, IRENA. So, so far we have seen why grid codes are important, why are they an enabling framework, and how they are helping the ongoing transformation of the power system. So today the focus of my presentation is to look at how grid codes have been evolving during the last few decades to include the new advancements that IRENA indicated is happening in the power system. So like IRENA mentioned again, grid codes must be formulated in such a way that the new innovations can connect without issues and causing issues, And if this is not done, then it actually restricts the addition of new technologies and new innovations. I will also try to highlight some of the examples from countries who have been spearheading this transformation of their power systems to a renewable powered one. But before we go, next slide, please, Sarina. So before we go to the new evolutions, let's take a look at some of the existing requirements regarding VRE power plants that are already being mentioned in grid codes all over the world. So the goal of grid codes is basically to ensure that we have a predictable behavior from all generators. And in the case of VRE, it is actually meant to help them to emulate the behavior of synchronous machines. So some of the earliest requirements include voltage and frequency operating ranges, which is a standard in every grid code that you can come across. They are one of the oldest requirements as well. Then moving on to frequency control capability requirements. This would actually be related to active power reduction or increase during inertial response, giving inertial response. Then VRE generating units may also be required to give frequency regulation results. This has not become obligatory in many of the grid codes that I mentioned it, but they are also catching pace. On providing reactive power support and voltage control, there are two aspects to this. One is to provide reactive support from the generator itself, and the other is to have the capability to implement different control strategies like power factor correction or constant power factor control. These are visible in almost all transmission and sub-transmission grid codes and also in distribution grid codes worldwide. In the case of fault behavior, it is basically to ensure predictable system behavior and to be resilient to grid faults. Protection is usually mentioned as the responsibility of the grid operator or of the project owner to see that the VRE power plants are protected and also to ensure that they are not overprotected in some instances. Then VRE systems that have been connected to the transmission network, they have been ensured, they have to ensure that they are SCADA enabled and they have SCADA enabled active and reactive power connection to the power system operator so that they can be remotely controlled and monitored. Another important requirement is about power quality, where there is the provision to actually limit the total harmonic distortion that happens at the point of common coupling. And most importantly, but which is very much in discussion now, is the VRE generation forecasting, which is seen mentioned in some of the advanced grid codes. They have been mentioned as the provision of VRE generation at least 24 to 72 hours ahead of the system operation. Next slide, please, Arina. So there is a clear change in the way, like Arina mentioned, there is the change that is happening in the power system is due to a lot of decentralization, digitalization, and electrification of end-use sectors. And because of all these changes happening, there are multiple distributed energy sources being connected at lower voltage levels, as opposed to earlier where it was connected at medium voltage or higher voltage levels. So the grid codes need to be evolving to include all of these new grid users into their purview. Now, storage is, for example, storage is a key enabling technology. Electromobility is expected to be a very represent a significant share of power consumption in the future power systems. So, and as Arina mentioned, which is very important, is that the grid code should not distinguish between technologies. So it will be more technology neutral, so that to avoid introducing technical barriers for individual technologies. Next slide, please. So the evolving trends that have been seen or visible in some of the advanced grid codes are shown here. So from extending application of existing requirement to small user, you can see there is mention of controllability, communication interfaces and integration, and low voltage right through. Whereas to new user types, there is a mention of storage and consumer producer combinations and electric vehicle charging. And adding requirements for new technical capabilities, you will find that there is addition of or mention of high voltage right through and grid forming capabilities of inverters. Next slide, please. Now, to discuss some of them in detail and to give some examples which we have seen in the grid codes in the near past, with increasing penetration of VRE, DERs being connected at low voltages, the controllability becomes very important. So there are two main facets to this. One is to reduce power output and one is to increase power output, and also to return to pre-fault conditions, but as demanded by the system operator. So the VRE must be capable of doing this. VRE power plants or DERs must be capable of doing this to the extent possible without mandating an additional storage connection. Then LVRT, like I mentioned before, was only mentioned for systems connected to high voltage and medium, but now it's made applicable to DERs that are connected to the low voltage grids as well. Now, high voltage write-through is something which describes the characteristic is something that describes the behavior of or the performance of the generation asset during voltage rise, and over voltages can be prevalent in many different situations. So it can happen during falls, it can happen during unprecedented large-scale tripping of generation or load, and all of this can actually affect or impact the trip or cause the tripping of DERs or VREs like wind turbines. And to prevent this, there should be grid codes which mention that the wind turbines or the VREs should remain connected during a certain stipulated time period of overvoltage. Now, this has been mentioned in some of the grid codes as well. In case of communication interfaces, coming to why communication interfaces are very important, because it's VRE integration is possible, or the different devices integration is possible only if you have an effective communication channel, and it is always better to have a standardized protocol or interface that requires to be implemented. Otherwise, it is not going to be cost effective for the DR operator or the manufacturer. And at the same instance, internet-based communication is becoming more popular and relevant, and because of which cybersecurity issues are also becoming critical to be tackled. I think there is a new network code that is coming up for cybersecurity, which is under development by NSOE. Next slide, please. So storage and other consumer producer connections have also seen mention. In Europe, particularly, the storage is considered to be a similar characteristics as generating unit. So they should follow all the requirements as a generating unit would. In the case of EV charging, recent grid codes have adopted certain norms for EV charging as well. For example, in Germany, when the EV is discharging, because EV is not a permanent connection to the grid. When EV is discharging, the German grid code stipulates that they should ride through the low voltage situation as any other generating unit would be capable of doing. And also the interface that is connected or through which the charging station is connected should be capable of bidirectional communication for a certain rating, above a certain rating, and for remote control and monitoring. Now, another important aspect that we would like to discuss is about grid forming inverters, and these are inverters designed to operate without an external voltage source, and they're different from the grid following inverters that are used in the current systems. And now there is a lot of discussion ongoing for the applicability of grid forming inverters in 100% VRE penetration systems. And that even though these have not seen a large scale rollout, there is a lot of discussion on it. There is a lot of research going on regarding the application of this. And I think the National Grid ESO from Great Britain has taken a first step to acknowledge this and bring out a draft proposal of grid code requirements for grid forming inverters. So I think power system operators are mostly of the opinion that sooner than later, grid codes for grid forming inverters should be put in place. Next slide, please. So every system is different, and one size fits all solution is next to impossible. So given the wide variety of country power systems, how do we see what is important for designing and facilitating designing grid codes and therefore facilitating VRE integration? So let's take a look at what are the specifications that we need to have a look. Next slide, thank you. So the technical connection requirements specified in grid codes can be divided according to the issues addressed, the definition of user classes, such as whether it's a generating unit or a consuming unit or a hybrid of both, power system sizes such as the voltage level to which it is connected, and also the capacity or the rating of the power system unit, of the generating unit, and of course the power system characteristics. So that means basically what we intend to say is that no grid code can be common to all countries or systems. So the basic requirement or specifications can be very similar, but there is a significant variation in the parameters and in the range of grid user facilities from system to system. And all of this must be considered when designing grid codes for systems in different countries. Next slide, please, Arina. So this is an indicative guideline of how requirements change with increasing shares of VRE. So these are not designed to match with any particular existing systems, but they bring together commonalities that are there or present in most developing countries. So the requirements basically should focus on including standard VRE industry standards, state-of-the-art VRE industry standards and rules that can be adapted from countries who have already achieved high shares of VRE integration in the systems. So, and countries who are actually looking at targeting at high VRE shares or are at the minimal VRE share inclusion at present should not make the mistake of actually adopting very lax grid connection codes, because later on when the VRE integration improves or you are increasing the VRE integration, there will be challenges which cannot be addressed by these lax connections. And of course, it is also costly to make retrofittive actions. So it's better to actually go in for state-of-the-art, up-to-date best industry practices at the moment. And next slide, please. So this is a non-exhaustive list of IEC and IEEE standards that generally describe the behavior of generating units, and they often leave enough room for implementing new functionalities as well. So this can be used to develop technical requirements and use them. You can use them as guidelines, and they're often referred to as in case of grid codes. So especially in terms of designing, installing and commissioning of generating equipment, these standards can be of great help. So with this, I close my presentation and I hand it over back to Arina. Thank you.
Thank you, Gayatri. Going further to the fourth key message, it's about regional grid code connection codes, which is key to facilitate international power trade and ensure competitiveness. Developing grid codes requires a lot of effort, so cooperation with others to share resources is often better, especially in small countries. Regional grid codes can basically help with improved market access for manufacturers of modern and advanced equipment at a low cost due to economies of scale, safer regional operation, and easier adoption of VRE share. Cooperation and coordination go through different stages. Historically, there were basically bilateral agreements that were focused on ensuring power system security in emergency cases. And mostly, was organized through bilateral negotiations and agreements. The nature of such cooperation evolved to bilateral trade of power to optimize the net benefit. And then the shifts towards open electricity markets, along with the introduction of increasing share of renewables, introduced a greater need for cross-border trading and TSOs coordination in neighboring regions, which gave rise to the introduction of regional grid codes in some cases, such as the United States and Europe. Regional grid codes ensure competitiveness in regional markets between assets connected to one grid that have the potential to sell their energy and services in neighboring markets. And the EU regional grid code requirements are basically minimum and non-exhaustive, which means that each TSO could specify additional or stricter requirements for each of the countries. One of the key challenges for applying similar set of requirements to all generators in the EU is the fact that there are 5 synchronous systems of different sizes. And frequency stability functionalities, for example, may be required from smaller generators if synchronous system is smaller and each individual generation has a higher impact in the overall system stability. That's why the difference between the grid code connection codes in different regions and different countries of Europe. Regional connection codes, however, often focus on ensuring operational security, as in the case of Europe, and focus somehow less on harmonization, actual harmonization of technical requirements. The last key message is an imperfect grid code is in many cases better than no grid code at all. And let's take a look at the steps of developing a grid code. It's not an easy process. First, policymakers need to mandate that grid codes must be written and need to define the scope and applicability. They need to appoint the responsible lead institution for developing these grid codes, and the lead institution, which is usually the TSO, the DSO, or the other parties, depending on the scope of the grid code, forms a working group and agree on a first draft of contents and assign tasks within the working group. The working group, of course, conduct studies, determine technical parameters, and draft the code. And then a consultation beyond the working group with other stakeholders is done to finalize the document, which then needs to be approved by the regulator or other administrative body to put it into force. Regular revisions of this grid code are needed to understand if the requirements are still appropriate or other rules need to be added or changed. Few key recommendations that we give for developing a grid code is to install a working group with a diverse set of stakeholders representatives from the very beginning, because no individual stakeholders has enough in-depth knowledge for all relevant technical details. So bringing on board all relevant stakeholders early on shortens the feedback loops and leads to a higher quality draft. Also, grid codes has an important role. This kind of process and this cooperative process in developing the grid codes have a very important role in building trust between different actors in the system. Also, overall coordination between various working groups that work on different grid codes and somewhat responsible membership overlap should be considered because just to ensure the systemic perspective of all the grid codes in a system. An imperfect grid code is in many cases better than no grid at all, especially when economic conditions allow for renewables energy development to pick up pace. In this situation, the development of grid codes or even a simple set of requirements that to be imposed to generators is needed quickly. And such requirements can be developed based on international experience or good practices, and they don't need to be perfectly suited to the needs of the system, but rather to ensure certain minimum functionality of new generators. And it is usually easier and cheaper to later reparameterize functionality and better reflect the needs of the system. Requirements can be evaluated and refined using more detailed power studies later on. Special care should be taken not to ask for excessive requirements that would turn into higher costs that would restrain the development of VRE. So I would like to close these insights with the fact that implementation of grid codes gives system operators confidence that assets connected to the system will not endanger the security of the electricity supply. And establishing a grid code is also a very important step in opening up the power sector to private developers and new plant operators, and enabling sufficient integration of distributed and large VRE generators. Thank you very much for your attention, and I will hand over back to our moderator, Martina.
Thank you very much, Arina and Gayatri. This was very, very useful, certainly. And well, sometimes this topic doesn't, or very often this topic doesn't receive enough attention. A lot of details. We will be posting the slides online so you can look through them. We are running out of time, so I suggest I will just ask you two questions, one each, and then we will close the webinar. So maybe that is better for Gayatri, this one. It's about ancillary services and whether these are addressed in grid codes, and also if you can maybe give us some examples on such services. Thank you.
Okay, thank you, Martina. So, thank you for the question as well. Ancillary services are routinely found in grid codes, but the difference is that there is no strict line between the grid code requirements and ancillary services. So ancillary services can be mandatory, they can be remunerated or required by grid codes, and it's difficult to provide. So maybe the grid codes can actually specify the ancillary services, but the actual provision of services are subject to some procurement scheme. So and some examples you asked is basically like examples can include maybe the capability to provide reactive power from all generators, but depending on the country or the region, the actual delivery of this may be remunerated or maybe activated on request. So that's one example I can think of.
Wonderful. Thank you very much. And maybe a question also for IRENA. So IRENA is like its membership is like a lot of countries are trying to quickly decarbonize their power sector. So how is, and grid codes are the part of the solution. So can IRENA help those countries develop the grid code connections? Yeah, can you a little bit elaborate on that? Thank you.
Oh, thank you very much. This is a good question. Well, we published this study to give overall guidance and to inform countries of the best practices and what they should take into account. But developing the grid code for a specific country, it's a very complex study, and it requires much more details and much more studies and details for the power sector. We have not done this kind of study focused on one single country so far, and this kind of requirements can be done directly to IRENA from each of the countries, and it's subject to availability of funding. Gayatri actually and Gayatri's team, which is grid integration team, are doing country-specific VRE integration assessment studies, and I know that they are also including in this general assessment study recommendations for grid codes modification. Gayatri, if you want to complement to this question, let me know. But
yeah, and Gayatri, maybe you can even like share the countries you covered. That might be helpful for our audience.
Thank you, IRENA, thank you, Martina. So the question about grid assessment studies, we have recently completed a study for the Republic of Mozambique. Even in that, we have provided a few recommendations based on system operation, because the grid assessment studies are network studies which tell us what operational measures can be changed or modified, or what constraints can be modified according to the situation of the grid and the inclusion of VRE, the share of VRE that's being included in the system. And similarly, we have also done studies for some of the island nations. To mention a few, we completed studies for Vanuatu, Fiji, and Dominican Republic most recently. And here too, we have provided some recommendations. I see a question in the chat that's asked if you could share with us a good grid code reference from countries within Asia Pacific region. I know that India has a grid code. Maybe it would be good to look at that example. And there are other examples from the Pacific region, like Australia is a good example of some of the recent practices being evolved or added to grid codes development. So maybe that's also good reference material. So like we mentioned in the report earlier, so more grid code is applicable to every country. It's system specific, and you have to take down the modifications. You have to adapt the existing grid code to your country specific requirements.
This was very useful. Thank you both. We a little bit over an hour, 30 minutes. So I would like to thank you both, IRENA and Gayatri, for your time and for sharing with us your knowledge and experience with market design, grid codes, and also all the challenges ahead of it, and importantly, some recommendation. And I would also like to thank all of you for joining us today, for listening, and for your questions. And we hope that you learned something new. And just what comes next. So we are planning already a series of webinars. So in our next webinar in 2 weeks, we will have a webinar on hydrogen trade. And then on the nexus of energy and agriculture, particularly with the use of geothermal. So we will be opening registration soon, and we look forward to seeing you again. Again, thank you all very much for joining. This is all from us for today. I wish you a great rest of the day. Goodbye and see you soon.
Thank you. Goodbye.